Okay. Thanks, Jeff and Eli, for inviting me. I appreciate that. So I'm going to talk packaging of new servers and talk about mainly some cooling. Since I'm mainly in the cooling area, I'm going to talk mostly about cooling, but I did borrow some slides, if you will, from the key architect on our high-end power systems, Ed Seminaro, so I put some of those in this. So let me jump right in. Liquid cooling, let me kick it off by talk about liquid cooling and how we're applying it across some of our products, and then I'll get into specifics on Power 6, and then even though it's not announced, I'll talk a little bit about Power 7. Obviously, I can't tell you everything about that, but I'll tell you a few things. And then as I was listening to everybody yesterday, I thought I'd throw in a few slides on data centers to end up here. So water cooling, we got back into it in 2005. And it's a very simple way to get back into it. It's basically a heat exchanger on the back of racks. Is there a light pin here? Does this work? Okay, good. So this is basically a coil heat exchanger on the back of racks, and the reason, and it goes on also the back of this rack. So the reason is we really had high-powered racks in data centers, and clients were having problems really dissipating that heat to air. It was creating hot spots in data centers, so we came out with this product that applies to any of our high-end P-Series products and all of our x86 products. So it was a simple way to get back into the water cooling after we stopped basically water cooling in the bipolar days. The last one we shipped out of Poughkeepsie, New York, and bipolar was 1995. So this was 10 years later. We got back into it. This is another product I'm going to talk about in just a second with a couple slides. This actually has liquid cooling inside it. It's refrigerated cooling. This is our high-end Z series mainframe, if you want to call it that. And we've been doing refrigeration cooling at the processor level since 1997. So we've lowered chip temperatures. We increased the performance of that first one that we shipped back in 1997 by about 7% by applying refrigeration, lowering chip temperatures roughly 30 degrees C, 35 C over what we could have had with air cooling system. So it's all internal refrigeration cooling. And then recently, which I'm going to talk more about, which is our Power 6 575, again, bringing water down to the processors. And I'll talk more about that. So here's our mainframe. Let me just kind of show the structure here. So here's the AC to DC power supply. So power comes into the system. Typically, these high-end systems bring 480 volts in, more efficient. So this is our power supplies. Here's our I/O cages here and here. Here's our condensing unit for our refrigeration. Basically, it's a compressor, condensing units, some valves, and so forth. And here's our KEC, which one of these, I'll say, boards, if you will, is shown over here, processor book. So you can maybe see some refrigeration hoses that go up to the KEC right in this region right here. So this is refrigeration cooled on the processor, and then we have DIMMs and so forth in that KEC. We also have battery, an option. You can buy battery backup, so you could unhook the system from the grid and roll it down the hallway, and it'd still be powered up for a short period of time. I just wanted to go back a little bit and show you our power trends on this Z series mainframe. This is over a number of years. This is back to bipolar days. This is about 1975. And we went to 1975. The last one, as I mentioned, was 1995. We shipped out of Poughkeepsie. You can see back then, water cooling was a big portion of our machines. This is like our last one, 80% water, 20% air cooling. Then the industry switched over. This was about early 1990s. The G4 came out in 1997. That started our refrigeration. And we've gone through refrigeration, I don't know, about eight or so generations so far. So a big change over the years. You can see 80 kW here, went down to about 2 kW. And now we're up to, on that 2-frame rack that I showed, about 27 kW. Essentially air-cooled to customers. Looks like air-cooled. So here, just want to show the pictures. The big bipolar days took a lot of footprint, a lot of area. Again, this was like 80 kW, and now we got this very small footprint, but now it's very high density in that very small footprint, 27 kW. So here's our product line. On the left, X series, x86 market, mid-range storage. Operating systems are Linux and Windows. Key competitors, HP, Dell, and others. Our major development site is in Raleigh, North Carolina. What I'm going to talk about is the middle column, just the high-end P I'm going to talk about, but high-end P and Z and high-end storage. We have our own chipset there out of our own development group and foundry. Several operating systems, competitors, a number of competitors. These mainly come out of Austin, Mid-Hudson Valley, Poughkeepsie, Fishkill, Yorktown Research, Rochester, Minnesota, Tucson. And then our Z series, again, our own chipset. Key competitors, HP and Sun, and principal development site is in the Mid-Hudson Valley. Way on the right, I'll say specialized high-performance blue jean systems, cell blades, competitors, Cray and so forth, development, Yorktown, and Rochester, Minnesota. So the one I'm going to talk about mainly is the high-end P right here. So here's our power system. If you say packaging, if you will, here's our P5, our prior generation. This is kind of the full package. If you want to look up here from the very low end, I'll say blades, all the way up to our high-end P series. Here's our P6 module set, if you will. The one I'm going to talk about is this P6575. It has about 800 million transistors on it. It's about a 450 millimeter squared chip. In this system, it's about 200 watts. 200 watts. This is for the water-cooled version I'm talking about. So this was announced in the first half of 08. The supercomputer show in 07, but actually shipped in 08. So a lot of effort to really make this as most energy efficient as we could. Try to, I'll say, gather up a number of system components so we can combine them on several components instead of many. Chill water cooling that I'll talk more about, that took out the cooling directly to chill water rather than go through a couple stages in the data center. Processors directly water cooled in this case, that took us another step, and lower temperature, lower leakage power. This particular box is about 2.5 times the compute power that we have in a full rack of blades. And this one that is out there on the market, and then we followed on with our next system, which is Power 7, and this one, first rollout of this would be University of Illinois National Center for Supercomputer Applications that I'll talk about. So here's the structure of the P6575. It has 14 nodes, and the power, much like we had what I showed in the mainframe, is on top here. So could have 480 volts coming in. And then we distribute 350 volts DC throughout the system. And we have 14 nodes. You probably can't pick it out, but there's water cooling manifolds up the side here, supply and return. And then at the very bottom is what we call a water cooling unit. water cooling distribution unit that brings in chill water. And then that chill water goes through a water-to-water heat exchanger that distributes that, I'll say, conditioned water to all the nodes. This shows a blow up of one of the nodes. It kind of has something like a car hood, if you will. So you can raise up the car hood, look inside of it. Power supplies are in the top, DC to DC power supplies. Water cooling cold plates on the processors here, 16 processor modules. You see the DIMMs here. Blowers on the front to take out the, I'll say, the excess over and above what the water cooling takes out. And you can see hoses come out at the front and then tie into these manifolds. Here's the water cooling version on the left, air cooling on the right. Of course, with water cooling, you can get much higher performance, 4.7 gigahertz versus the 3.5. You see similar structures, same board layout. Of course, these are air-cooled heat sinks. Blowers are a little different form factor, but much of the packaging looks much the same. Here's a symbol node, a little more clarity. I think you can see the cold plates here. All 4 of them are in series. 4 of the processor cold plates are in series, so there's 4 groups of 4. 16 processor modules total. 2 core processor chips. 32-way in a node. So here's the cold plate assembly. This is all one structure. Because of planarity concerns, we had to put this all together as one. The bends in the piping are really to relieve stresses, if you will, down at the processor module. So these were very carefully laid out. A lot of work went into that. Hoses then come out the front and then tie into the manifolds on both sides. This is the secondary loop. So this is a schematic of what I kind of described before. Here's the modular water units or water cooling units at the bottom. They are redundant. So the water's distributed through all these nodes. And then what is not taken out or what's remaining is taken out by a rear door heat exchanger that I showed you in that first slide or so on the back. So here's kind of how the heat load is taken out. The processor is about half the heat load. The rear door heat exchanger on the back about 27%, and that what's remaining, about 20%, goes out into the room. Here's the water cooling unit, and I'll talk a minute about that. The next one. So it has all the, I'll say the standard stuff: heat exchangers, control valves, magnetically driven pump, reservoir tank. Chill water comes in on one side, control water comes out on the other side to the nodes. This unit handles, compared back to the bipolar days, the bipolar cooling distribution unit for the same heat load typically was about like this, maybe 3 foot square and about 6.5 foot tall. This now is 4U tall for the same heat load, 4U tall, about 11 inches wide and about 30 inches deep. So we've really not only improved by much all the electronics, but from a cooling standpoint, this is much improved what we had compared to bipolar days. This is how we put it then in a data center. So this is a cross-sectional view showing the raised floor. Cable trays here. Facility water comes in these pipes, and then hose tie in basically to the water cooling unit in the back here. This would be the rear door heat exchanger in both these locations. The fronts of the machines are here and here. Power cords underneath, redundant power cords, so we lose any power cord, we still continue operation of the machine. I talked about 480, three-phase power connection, line cord redundancy. No PDU losses because we don't have that, eliminated that. Lower building distribution, if you use 480, you can probably gain 2 or 3 points on a building by using high voltage AC. direct building chill water, I'll show you this. We save probably 20% on cooling energy by going to liquid versus air cooled, compared to computer room air conditioner that had large blowers and contribute a lot of, I'll say, energy to run those blowers. It enables tight packing. This is kind of key, because if you have tight packing, you can put a lot in a data center, but with air cooling, you do have that problem. These large heat loads, it's very, very, very difficult to cool these large heat loads if you had them stacked like we normally do in a data center. So water cooling takes out that, I'll say, that hotspot problem. Here compares to P5 to P6, so this is one generation. This was our P5 air-cooled machine, 35 kW max. Now our water-cooled machine, that same, I'll say, footprint, 85 kW max. It's typically shipping more like 60,000 watts. In this form factor compared to what we have on 6x density of, I'll say, P6 sort of standard hardware, P6 hardware that you could put in, or 3x P6 blade servers. Some other metrics down here. Here's the Lawrence Livermore P5 that we put in several years ago. ASCII Purple was called. It was 100 teraflops. It was near the top, or maybe it was the top. Supercomputer, 137 racks. Now we can do that in 12 racks, or about 1/10 the space. 100 teraflops. 45 milliwatts per megaflop compared to 8 milliwatts per megaflop here. This was all 100% heat load. And again, that's difficult. Can be done, but difficult. You'd never do that air cooling in a data center. So much better thermal. 80% of the heat load goes to water, 20% to air. Here's a real quick, don't look at all these numbers, I just want to point out a few of them. This happens to be the National Center for Atmospheric Research in Colorado. 11 of these machines are out there. And if you just compare, I'm going to point out a few numbers. If you take an air-cooled system of the same form factor, 16 versus 12, this is the same performance as compared to 12 water cooling. 16 air will be the same as 12 water. Total electronic power on the air is 976 kW. On the water, it's 864. So there's a big difference right there. If you look at the air-cooled system, all the infrastructure to support the air cooling, chillers, cooling towers, crack units, all that, it's 365 kW to support that 976. For water cooling, it's 209 to support the 864. Just on the cooling energy, it's about 40% reduction in the data center. And on the total energy, if you include electronics and cooling, it's about 20% reduction. So big improvement on energy savings, looking at the whole problem. So let me jump forward here and talk about the new systems we're working on. This is Sequoia's system. Some of this is on the web, so you can find this. Be out in 2012, 1.6 million power processors, 1.6 petabytes, 20 petaflop machine. Blue Waters, this is the one I'm going to talk about. University of Illinois, NCSA. We're talking about a petaflop, but it's petaflop plus sort of system. So this is being built right now. It's a new data center at the University of Illinois. It's a grant from National Science Foundation to put this together. And again, this is built on the Power 7 architecture. This is a layout. This is about what's shown here, about 150 racks, something like that. So we did really carefully look at the whole design here, all the way from the ambient all the way into the processors when we put this together. So the idea was, how can we make this the most energy efficient that we could? So we looked at server storage and networking, power conversion from the 13,000 volts that comes into the building. How do we distribute that to make it most efficient? Heat removal, basically we're taking all the heat load out at the rack. So we won't have really any need. There is some, but any need for computer room air conditioning units in the data center. High availability design for the infrastructure. We have multiple feeds from substations on the campus. And of course, we're packaging everything very tightly, so minimum waste of floor space. Move more to integrated large-scale IT equipment, integrate the network, unifying the storage and servers, eliminate unnecessary data flow and protocol conversions that burn power. Try to gather things up and combine them in components that are very energy efficient. Integration reduces IT equipment hardware content, yielding better reliability and lower cost. Improved heat transfer. We spent a lot of work on this, trying to pull this together on how do you really package this and start to do water cooling more across the whole system than what we had done on P6. And higher temperature. We do allow up to, now the water temperature, up to 15 degrees C or 60 degrees F into the system. So that also saves energy back at, I'll say, what delivers the water to the systems. Eliminate majority of the room air conditioning units, so we don't have those big blowers blowing, I'll say, air conditioning into the data center. Those are typically large horsepower motors. Distribute high voltage in the data center. This is really important. High voltage is all over, so let's just use it directly to our servers. Either ship around 400 to 480 volts directly from the output of the building transformer, or you can take 400 to 600 directly from the output of the UPS without having that inverter stage. No on-floor step-down transformers, low loss cabling, efficient building transformers. We can get very high, near 99%. UPSs, I think a number earlier was mentioned, 92 to 95. And if you take the DC output and eliminate that last inverter stage, you can get up to 97%. So into our system then, we could potentially take AC, anywhere from 200 to 480 AC, or we could take 400 to 600 DC. Doesn't depend on anything. We can take either one of these. And we could, for smaller systems, take 277 volts AC, take out from phase to neutral on 480, and ends up being the 277 as another option. Again, the key here, design IT equipment, power and cooling for true end-to-end efficiency. Go all the way from basically 13,000 volts into the building down to 1 volt or whatever, down to the chip. And how do you do that most efficiently? So we looked at that whole train and tried to determine what the best components to do that. Lower temperature on CMOS, I mentioned that. We'll have lower leakage power that will dissipate less to the water cooling. And electronics, definitely, this is packed very tightly, and probably will end up dissipating less power by doing that. I want to mention this, the PUE, kind of I'll say somewhat of a standard in industry. PUE, power usage effectiveness. It was coined by the Green Grid here, I don't know, a couple of years ago, but very simply, total facility power, total into the building, I'll say, divided by the IT power is how it's defined. So for this one, for this data center, this would be about 15 megawatts of IT load. And looking at everything, we've calculated we're about 17.6 megawatts in, which calculates out about 1.18 PUE. Compute cabinets, as I mentioned, 100% water cooling. I think I've talked about all those others. So now let me switch over again a little bit to data centers. I think these, in different forms, I think different people have presented up here have shown these numbers, but let me just put my chart up here, I guess. So here's the electric use in the US. Residential and commercial is growing about 8 to 10% every 5 years. And industrial is about flat. If you remember, Jonathan Kumi earlier this morning showed 60 billion kilowatt hours per year, about right there, that number. And if we grew double every 5 years, which some people started to say, here's what it looks like, which is, this is really scary then, because if we end up doing this and coming out, that would be a huge impact to us, right? This is a scary chart. So we all got to do our piece on trying to bring this curve down. Other people have shown this, and this is, when I always look at this, I always think, oh my God, this is not good. Here's our server. This is one I showed you, right? Here's the chip. Basically, the bottom line is everything that does the work out of these machines is that silicon, right? And you can almost, these big machines, you can almost put a lot of the silicon in your two hands, everything that goes in that machine that does all the work. But all that other stuff is to connection and cooling and everything else, right? So everything put in your two hands, 80 kW, okay? So I'm trying to cool and power that 80 kW and cool it. These are all the things that take place. Here's the computer room air conditioner, the blowers. Then I tie into the building chill water with pumps. Then I tie into the refrigeration loop, has compressors. Then I tie into the cooling tower that has pumps that pump that water. And then I tie into the big blowers that actually exhaust heat load back out to the environment. So all this basically to cool that handful of chips to 85C. So I always think, God, if I could get all our developers to walk around these data centers and look at all this extra stuff, because there is a lot of extra stuff. There's the data center. That's kind of what our developers think, you know, that's it, right? This is all we, but all this other stuff, chillers, diesel generators, batteries, crack units, cooling towers, static transfer switches, UPSs, it's all this other stuff really contribute to making this rack work. So it's like every watt you start building this stuff. Somehow, let's stop this, right?
You can put that behind your curtain.
Yeah, and that's what happens. That's what happens. The tours always happen here. You never see this. This is another gee whiz chart. It's one of these systems, I'll say air cooling, roughly 30 kW from where I come from in Poughkeepsie, New York, will heat a house. One of these systems, 30 kW. We're now at 80 kW and probably going higher. Another thing, these are heavy systems. One of these systems weighs like a car, and we put them up, stack them in like the table here in front, one after another. So another concern absolutely is the structure that these systems go in is really something you got to be concerned about. So a couple more slides and I'm going to quit. So not everything obviously is going to be liquid cooling, so there's a lot of air cooling designs out there on how do I design this into data centers. I'll say this is kind of more the typical where you come in to the cold aisle. We call it cold aisle. So the fronts of the machines face that cold aisle, and then the cold air washes the fronts of the machine, goes out the back, and then back to the crack unit, which is the air conditioning unit. That's kind of, I'll say, a typical setup, but there's more out there that are ducted flows and various baffling that may occur. Here's a rear door heat exchanger that takes out a major part of the heat load. So a number of things out there. Best practices, just don't mix the hot and cold air. Don't allow that to mix. So you have the best energy efficiency at the data center. And let me just, if I can make this work. Okay, this is just, these are 4 racks. Here's 4 racks. The air conditioning unit is right back here. So the cold air comes up from the bottom, goes in the machine, comes out the back, tries to get back to there. The concern is with the higher and higher powered machines, you cannot supply enough chilled air to these racks. It's just, it's gonna start pulling air from wherever it gets it. And what happens is the hot air that comes out the back typically kind of curls right over the top, and that hot air goes right in the front of the machine and can shut the machine down. So that's a major concern in data centers. So the way we used to do maybe 10 years ago, just roll in a rack and just don't worry about it, you can't do that today. You really got to engineer the solution. So liquid cooling is back, proves overall energy efficiency. You can get much more compact designs, pull things together very closely, integrate functions more effectively to drive efficiency. We've been viewing the designs more holistically, all the way, I'll say, from the outside to the inside, both from a cooling and power standpoint. So with that, I'll stop. Thank you very much.
Thank you, Roger. Questions? I'd be curious to know about containing a liquid failure. If you have a little leak at a single processor, can you say how the systems are designed to limit how far that leak can extend?
Yeah, great question. We never allow leak. So let me give you a little history because I think that's appropriate here. So on bipolar days when we did the cold plates, again, we started water cooling in 1964. So we've had, what's that, 50 years, 45 years sort of working in this area. So we never had a cold plate fail ever. Yeah. So you really don't want that to happen, what you just brought up. You want to put enough quality processes in place that you can't have liquid dripping all over your electronics and stuff like that. So yeah, we put a lot of quality in place and different things to make sure we don't have anything happen, I'll say, in the node. Now, outside the node, you know, underneath the floor, people nick stuff and stuff, things may happen there, but inside the electronics, yeah, that's a no-no for us.
Okay, so in your data center, you must have you have the server and the networking equipment which hook up all these servers. Do you have the ratio for the power consumption between the server and the networking equipment?
I don't know that. You're talking about our own data centers?
Or the box you described.
Well, I don't know that number. Let me just give you, and this doesn't answer your question, but we operate about 8 million square feet of data centers around the world, about 500 different data centers. So as you can imagine, there's a lot of power being used in those. And I know we have that number, I just don't have the number. So we are very, very carefully, as you can imagine, because the energy that costs to run these data centers, we are very meticulous on going through and how we can save money. So we look at every aspect of it. It's just I don't know what the division is.
So obviously in the very big installations you're talking about, people are going to be willing to do liquid cooling and do all the plumbing and stuff. Well, what do you think the ratio will be between how many people are actually willing to do plumbing versus they're going to say, don't bother me, just give me air cooling?
Yeah, another great question. Well, and I wasn't around 64, but I'll just tell you when we first got into liquid cooling back then, it took probably 3 or 4 years to really educate the industry. Yeah, this is electronics and liquid, it does work. I think it's kind of happening again this time. The guys that were in the bipolar water cooling, they don't have any problem. They said, what did it take you so long for? The guys that were never in it are still saying, a lot of them, don't ever come talk to me about liquid cooling. So I think there's two camps, but I think what's going to happen is as we get more and more liquid out there, the word's going to go around, they're going to start talking to one another. And I think the liquid will start to go into those accounts that only have used air cooling. I think that's what's going to happen. But it's two camps today. The guys that have used it, they're very comfortable with it.
Is
Is there any notion of recapturing some of the waste energy?
I knew this was going to come up.
Whether or not the hot water going back is being used in the facility or even heat exchangers, whatever.
Yeah, great question, and one I get asked all the time. The problem with in these systems, the water temperature is so low, so it's really low-grade heat. You know, it's probably the return temperature, I'm going to say, I don't know, it's probably 25 C, which is like useless. However, we are, and I can talk about this because it is public, the Zurich Research Lab is doing some work in this area. So just think about this. The bottom line is we want to keep the silicon, let's just say 85 degrees C. And the heat sink now, let's say it's air-cooled in the count. Let's say it's 32 C. So you got like, what is that, 50 degrees C to work with. So if I could increase all those paths inside that package, where I could now, let's say, bring water at a high temperature and still cool to 85, because you got to do the 85. So let's say I can get, I'll say, 60 degrees C water and pass that in and still maintaining 85 C junction, then you got something that's useful. So there's some work going on in that area. Yep.
So you chose actually to use the rack as to be kind of the autonomous unit, right? Basically do the cooling at the rack level and basically make it self-contained almost. Other companies have chosen other granularities. For instance, Sun has been looking at container-sized type of units.
Yep.
Other ones are obviously looking at the building level. So what's the trade-off there that you see?
Well, a hot topic today, containers, and we have ours too, like probably every company that is in this area. There are trade-offs. It's pros and cons. I don't think it's for everybody, the container. I think you really got to, on the big data centers, whether it really scales well, I think is maybe a concern, right? Because now you got littler boxes rather than, you know, if you got a 30 megawatt data center, is that really the right answer? Although some are doing that. So I think this still has to play out. The containers are, I think, just starting to get into the market. I think we're going to see how this plays out. Yeah.